Hi, welcome to Carbon Cycle, and here we go.
Lately, we've been hearing a lot about global warming and words like carbon footprint, climate shift, carbon dioxide, and climate change. But what is carbon, and what does it have to do with climate change? Carbon is everywhere in the ecosystem, and it is always moving. Some of it is floating in the atmosphere. Plants absorb carbon from the air and store it in their bodies. When animals eat plants, they eat carbon. And when something bigger eats those animals, they're having a carbon snack too. But that carbon won't stay still for long. When an animal poops or something dies, carbon moves around again. Some of it is held in the soil for a while, and eventually most of it ends up back in the atmosphere. The same type of process happens in the oceans too. Most of the carbon dioxide gas on Earth is actually dissolved in ocean water. Some of the carbon from dead plants and animals was trapped underground, and over millions and millions of years it turned into coal, oil, and gas. And that's pretty much how the system works. Some carbon has stayed deep underground for millions of years, but the rest moves around the ecosystem from the air to plants to animals and back into the atmosphere. And that's the story of the carbon cycle.
So we're going to look at how carbon moves through the cycle, and we're releasing carbon that's been trapped for, millions of years, and how that's affecting our atmosphere. So basically, CO2 is stored in living things and is used, and then when you die, it's released and set back out. I mean, it's literally a cycle like the water cycle. It's trapped in plants, and they use it to create food, and then something eats it, just like the video showed. So plants use it to make sugars, starches, carbohydrates, and oxygen out of carbon. Fossil fuels then are the stored carbon that, as we burn it, we release it back into the atmosphere.
NASA has shown us that ours is a precious planet.
NASA has unique capabilities because we have the point of view from space. With NASA's carbon monitoring system, you can see the amount of CO2 in the atmosphere decreasing in the spring and the summer. Plants of the oceans and the land surface are greening up and pulling the carbon dioxide out of the atmosphere. And then in the fall and in the wintertime, you'll see the CO2 in the atmosphere increasing because plants and animals are releasing the carbon dioxide that was captured during the growing season. There is a graph called the healing curve where you can see the summer and winter cycle. The process is very natural. Contrast that with old slow carbon. So this is a chunk of coal. It was also made by plants. It also contains carbon dioxide that was in the atmosphere. But the carbon in this chunk of coal was taken out of the atmosphere 350 million years ago. And since the Industrial Revolution, we've been taking it out of the ground and using it for fuel. The burning of fossil fuels, whether it's coal, oil, or natural gas, has released this very, very old carbon back into the atmosphere a lot faster than the oceans and the plants on the land can take it out of the atmosphere. It's bit by bit moving the healing curve up. In 1989 was the last time we saw 350 parts per million. And it appears that 2016 will be the last time that CO2 is dipped below 400 parts per million. And what the heck is 400 parts per million? What does that even mean? Well, we know from the analysis of ice samples from Antarctica that before the Industrial Revolution, the amount of carbon dioxide in the atmosphere was about 275 parts per million. It had been this way for
Here's the
about
Industrial Revolution right there.
something has increased the number from 275 to 400. We're quite certain that that is due to the human activity of burning fossil fuels.
I take these satellite measurements and the variation over time, how the world's changing, as facts. We see this warming over the last century and a half. Very, very meticulous measurements. And it shows a really sharp acceleration in the warming over the last 4 decades.
People have a hard time understanding what's a big deal for a planet that is warmer by a degree, 2 degrees Celsius. That the impacts that we're worried about are being triggered not at a 20-degree warmer world, but they're being triggered at a 1-degree warmer world.
Over the last decades, we've seen the ice melting. We've seen the ice melting at the North Pole. We've seen the ice melting really fast on the Greenland, where it's falling off into the ocean.
We have Pacific Islands that have already had to be abandoned because of sea level rise. We can combine our data to global climate models and say, how is sea level going to change over the next 5, 10, 15 years? Because if we continue on the path we're doing, there's going to be a lot of coastal communities all around the world that are going to be flooded.
As scientists, we're just taking the most precise data that we can. It's open data, it's factual. For instance, enormous droughts and fires that we have around the world.
Like in Australia last year.
Planet. That has a huge impact on people. It's unprecedented.
We have a warmer atmosphere that can hold more moisture. That's what warmer atmospheres do. They can suck up more moisture. That means more convection, more big thunderstorms, more hurricanes, more extreme weather. That's the likely outcomes of a warming world. We built our civilization around the current climate, our coastal cities, our food resources, our water resources. They're all pegged to the current climate, and there's not much slack in the system.
We're already seeing that has an increase. In a 2-degree warming world, there'll be more. In a 3-degree warming world, there'll be even. And when you're looking at those kind of scenarios, 3, 4, 5 degrees warmer, which are totally plausible, if we go down that path, we'll be looking at it differently.
Okay, so this is one last video for this section, which is keeping up with carbon. Possibly. There we go.
Carbon is the basic building block of life, and these unique atoms are found everywhere on Earth. Carbon makes up the Earth's plants and animals, and carbon is also stored in the ocean, the atmosphere, and the crust of the planet. A carbon atom could spend millions of years moving through the Earth in a complex cycle. Understanding the carbon cycle and how it is changing is key to understanding Earth's changing climate. On land, plants remove carbon from the atmosphere through photosynthesis. Animals eat plants and either breathe out carbon, or it moves up the food chain. When plants and animals die and decay, they transfer carbon back to the soil. Moving offshore, the ocean holds huge amounts of carbon, about 50 times the amount we find in the atmosphere.
The ocean is sometimes called a carbon sink, meaning that it absorbs or takes up carbon from the atmosphere. It takes up carbon through physical and biological processes.
At the ocean's surface, carbon dioxide from the atmosphere dissolves into the water. Tiny marine plants called phytoplankton use this carbon dioxide for photosynthesis. Phytoplankton are the base of the marine food web. After animals eat the plants, they breathe out the carbon or pass it up the food chain. Sometimes phytoplankton die, decompose, and are recycled in the surface waters. Phytoplankton can also sink to the ocean floor, carrying carbon as they descend. Over long timescales, this process has made the ocean floor the largest reservoir of carbon on the planet. Most of the ocean's nutrients are in cold, deep water. In a process called upwelling, currents bring nutrients and carbon up to the surface. Carbon can then be released as a gas back into the atmosphere, continuing the carbon cycle. By cycling huge amounts of carbon, the ocean helps regulate climate.
So when you think of climate, you don't often think of the ocean. Climate, you think of, is it going to be hotter this year? Is it going to be colder this year? But the oceans are actually a great regulator, controller of Earth's climate. And they even are controlling how much carbon is in the atmosphere, which can slow down how quickly climate change is occurring.
At the most basic level, the balance between incoming sunlight and outgoing heat determines the Earth's climate. Greenhouse gases act like a blanket and trap heat in the atmosphere. Carbon dioxide is a greenhouse gas. In the past 2 centuries, humans have increased atmospheric carbon dioxide by more than 30% by burning fossil fuels and cutting down forests. The Earth has not experienced carbon dioxide levels this high for the past several million years. Researchers are learning that future climate change will depend on carbon levels in the land, in the atmosphere, and in the sea, and how these levels respond to human disturbance. About 1/3 of all human-generated carbon emissions has dissolved in the ocean. More than 80% of Earth's added heat is now stored in the ocean.
In the future, as the planet gets warmer, the water's going to warm up, and warm water can hold less carbon than cold water. The other thing is, on a warmer planet, some of the currents are going to slow down, and so we might not be forming as much of this cold, deep water. So we won't be able to transport carbon into the deep sea. So on the whole, the ocean's going to become less effective at removing carbon from the atmosphere.
Throughout most of Earth's ocean, the warmer water, weaker circulation, and new temperature gradients that result from climate change will impact marine life and ecosystems. These changes affect the ocean's ability to store carbon. Increased carbon dioxide in the atmosphere impacts marine life in other ways.
As the ocean absorbs more carbon dioxide, it becomes more acidic, and this can be a threat to some of the organisms that live inside the ocean.
Like
As Earth's
corals
climate
or shells.
continues to change, how will researchers monitor something as big as the ocean and something as complex as the carbon cycle? NASA Earth observing satellites give scientists the big picture view of our home planet. Varied satellites help researchers detect changes in ocean climate and ecology over time, providing vital insight into the health of our home planet.
So, as always, if you want to go back and look at any of this, there is a set of notes that I took this from, and you do not have to watch the whole video again if you want to look. Thank you for paying attention.